The next speaker is Joe Minahan, who's going to tell us about the Hagedorn temperature for integrable gauge theory.
All right, well, thank you very much for the organizers for inviting me to give this talk. I've enjoyed the presentations both in New York and here. I've actually learned quite a bit. So today, what I want to do is tell you about some work done with my, at the time, very excellent graduate students, but now who are young postdocs in London, Simon Eckheimer and Charles Tull. So there are two papers, and another paper is, well, I was more optimistic that I had a 4 in here before, but now I changed it to a Y. I didn't change the 2 to a Y either, but so I hope to finish it during the Trump administration. Anyway. In any case, I guess this doesn't work. I have to use this. So integrability is a very powerful tool for computing physical observables in planar n equals 4, and especially at strong coupling. So not too long ago, Harmark and Wilhelm used integrability basically to study the Hagedorn temperature at weak coupling, at both weak and strong coupling. And so using modern techniques called the quantum spectral curve, they generated this plot for the Hagedorn temperature as a function of the 't Hooft coupling lambda. Okay, so integrability people like to use, instead of lambda, they like to use this parameter g, where g is the square root of lambda over 4 pi. So in any case, at weak coupling, they found that the Hagedorn temperature behaves like this. So this number here was known since 1999. The next term in this expansion was found in 2002, I believe, and then but then they generated the next 7 or 8 terms using integrability. But most of this talk today is actually going to focus on the other side, where the coupling is strong. And unfortunately, and it's still the case, that using all these integrability tools, we still really only know how to do things numerically and not analytically. So all the results are basically presented like this. So at leading coupling, and strong coupling, you find that the Hagedorn temperature has this sort of expansion, and this is what these people found up to this order. So here's this expression again. So actually, this first term here, you can read off basically from the flat space limit in the ADS-CFT. I'll say a little bit more about this later. Okay, the next term is basically a curvature correction from a winding string on a compactified Euclidean time direction found by Juan and Arez. I saw Arez up there. We've actually improved the numerical results that they had. And this is what we have. And the purpose of this talk, I'll give some analytic results for these last 2 terms. Okay, and I'll also discuss some ongoing work to generalize these results.
How well do these large and small g expansions match each other in the middle?
Sorry, large and
small g, you have 2 expansions.
Oh, yeah. No, so these numerical results,
Yeah.
sorry, so these graphs I showed here. Wait, no, this doesn't work. Okay. Wait, where we go? Doesn't want to go back. Oh, there we go. Okay. So this result, this is done numerically starting at 0 coupling. Okay, but you can then see that you also will match this. Okay, so you can actually compute this, but you can see that this matches. So in particular, it matches in the middle where you're in the intermediate coupling.
It's reasonable.
Yeah, so up here you're in the string regime, and down here you're in perturbative, the normal perturbative regime. So anyways. So it's natural to assume that the Hagedorn temperature is related to the deconfinement temperature. But you might wonder that n equals 4 is a CFT, so it cannot confine. There's no confinement scale. But what you do is you can get around this and basically put the theory on an S3. And then by Gauss's law, you can't have a net SUN charge. So in a sense, the radius of the S3 sort of sets the confinement scale. And so at low temperatures, you find that the free energy will be of order 1. but at high temperatures, the free energy scale is n squared, and there's sort of, in the large n limit, there's a sharp transition between the two, and this transition is almost certainly a first order phase transition. Yeah.
What do you mean by related to the confinement? What the relation is just inequality, that's what you mean? Hagedorn is bigger than that's all you mean?
Well, okay, so at zero coupling, they're the same, they're equal. Okay, at higher, if it's a first order phase transition, then at non-zero coupling, it'll be, the deconfinement temperature would be below it.
Yes, so just an inequality, that's what you mean?
Yeah, it'll be an inequality. It's an inequality at zero coupling, but it's an inequality. Unless it were a second order phase transition, but it's probably not. So, it's almost certainly not. So, although I don't believe there's an absolute proof for that.
For SU2, it's second order.
SU2 is second order, but I'm looking in large N, so. Okay, so, but the way you can sort of think about this is we have a map we can do a map from R4 to R cross S3, and then the operators that you have on the R4, you can map into states, certain states, and then the dimensions of these operators map to the energies of these states. So for an example, we can consider computing the Hagedorn temperature at zero coupling. Okay. So this was a computation first done by Sundborg in 1999. So what we want to do is we want to consider all possible single trace local operators. So these would be given by some trace of some fields, labeled by up to where we have L of these fields. And so the partition function for this single trace operator, we basically sum over all possible lengths starting at length 2, because this is SUN, so the trace of a single field is 0, and sum over all the different possible single trace operators we can make, weighted by e to the minus delta over t, because delta is the energy now on this field. And Sundberg sort of thought of this problem as having beads on a necklace. And so we have basically 3 different types of fields. We have these scalar fields. We have the scalar fields here, phi I, where I runs from 1 to 6. We have these fermionic fields, and we have field strengths. And we can also have symmetrized covariant derivatives acting on this. So it's basically, again, just a counting problem. And so we have to also take into account the equations of motion, namely that d squared, we take d squared on the phi i's, we get 0, and we have similar equations for all the other fields. And so, for example, if we compute the partition function for a single bead, okay, we would count the possible number of, say, for the scalars, we count the possible number, so there's 6 possible different scalar fields, weighted by this y squared, where y defined by e to the minus 1 over the two types of temperature. And then I also have to take into account the part coming from the symmetrized covariant derivatives acting on this. And this gives us this term here. And this term here subtracts off the parts from the equations of motion, and we end up with this expression here. And you have a similar one for both for the fermions and for the field strengths. And you add up all these different partition functions for each of the beads, and you get this expression here. And then the partition function then for all of the single trace operators, you basically want to, it's more or less, it's not exactly this, but for our purposes, this is good enough. It's basically 1 over L times the partition function for the bead to the Lth power. And the 1 over L is there because what you're calling the beginning of the necklace is undefined. Okay, so you should divide up by that term. Okay, so in this case, then you can easily do this, and you find that this thing is the log of this, and this diverges when this is equal to 1. You solve the equation, and you find then that this divergence happens at this temperature called the Hagedorn temperature, which is given by this number. Okay, so notice that this Hagedorn temperature is set by operators with large dimensions. So as I was saying before to Zora's question, so at lambda equals 0, the Hagedorn temperature is the deconfinement temperature. This was shown by Sundberg and also by Ofer et al. And this is even true for pure SUN, deep in the asymptotically free limit, okay, because since we're on the sphere, we can, so we have some QCD scale, lambda, okay, if we take the radius of the sphere to go to 0, then this becomes small, and we go into the weak coupling regime, and you can basically still do the same sort of counting. And then Ofer et al. Showed for this pure SUN theory that for lambda greater than 0, that at least in the perturbative regime, that this deconfinement temperature is less than the Hagedorn temperature. But we also know for strong coupling using ADS-CFT that the deconfinement temperature is basically equal to the Hawking-Page temperature, and this is of order 1, while the Hagedorn temperature is going to be of order lambda to the 1/4, and clearly this is going to be much less than this at strong coupling. So anyways, assuming that n equals 4 behaves qualitatively the same as pure SUN, this Hagedorn temperature is the upper bound, basically, at which a metastable phase can exist. So you should think of the picture this way. We have some order parameter phi, which is more or less the Polyakov loop order parameter. And so if T is less than the deconfinement temperature, then deconfinement would be up here, okay, and this has lower free energy, okay, so here we're in the confined phase. If T is between the two, then we have we would have a graph, we'd have a plot that goes up and then comes back down, okay, and this is lower free energy than that, okay, and so the deconfinement would be, the temperature is greater than deconfinement but less than Hagedorn. And then if we're right at the Hagedorn, basically then we have something like this, and so this sort of metastable phase disappears. Okay, so you can't be in there at that point. So that's the way you should think about it. So from now on, I'm basically just going to talk about Hagedorn. Okay, so I'm not going to talk about deconfinement. Okay, so anyways, so we used the quantum spectral curve, and I don't have enough time to say anything about the quantum spectral curve, okay, and it's very technical, and it's probably, you wouldn't be that interested in it anyways, but the end result is that we improved on the numbers of the plots of Harmark and Wilhelm, and so you can see that we have some dots here that look sort of purple. So red and blue, okay, so they're not like swing states, but actually the blue underneath, okay, this is the Harmark and Wilhelm results, and the red on top are our results, okay, but the main thing we were able to do is we could go to higher values of the coupling, okay, and actually it's much more computationally intensive to go to large couplings, okay, so it basically took us a cluster to go from here up to there. Okay, but actually having that amount of extra terms here, okay, we were able to actually improve the numerics quite a bit. Okay, so we know sort of the leading two terms. So what we can do is we can basically just subtract them off and then get the next two terms. So these dots here are the results, the numerical results subtracting off this function. Okay, and this blue line here, this is a fit to this curve here. Okay, so so these are our results. You can more or less assume that the errors on this are to order are of 1 in the Okay. All right. So now let me try and explain where these come from. Okay, so we know that the Hagedorn, so we're in the strong coupling regime, okay, and so we should be dual to string theory and ADS 5 cross S5. So, but this is going to be thermal ADS, and so we're going to have a complex thermal scalar with a mass m squared beta, and the string winding modes W equals plus or minus 1 will wrap around the thermal scale circle of circumference beta. Okay, so to 0th order, basically, we're going to forget about the curvature. And it's when this thermal scalar has 0 mass is when we hit the Hagedorn temperature. Okay, and then antiperiodic boundary conditions for the fermions lead to a 0-point shift on the string Wolff-Sheet. Okay, so you can just use open up Polchinski and take consider type 2 closed winding string states. You find that the mass squared looks like this. And so beta of h, excuse me, is equal to this. And then using the ADS CFT dictionary, where alpha prime is equal to 1 over the square root of lambda, which, remember, we're using this g, is 1 over 4 pi g, you find out that the Hagedorn temperature is this result right here. Okay, so that's the first term. So the second term was explained by Maldacena and Urbach. So to do that, we can consider a Euclidean ADS5 metric. So we have, so I'm going to use this metric here, where tau is identified with tau plus beta. This is my thermal circle. The winding mode should be a light complex scalar chi, okay? And so its action would basically have this form here. So we can just consider its kinetic term and the mass term. But the mass term, basically, since the string is winding around this thermal circle, okay, as we move away from the origin, sort of the length of this winding mode gets bigger, okay, and so that will sort of increase sort of the energy of that state. Okay, so we have to take this into account, and so this m squared, this mass squared term actually has some r dependence, where r is sort of the radius up here, and so we would expect it to be to have this form, and then there's a shift. Okay, and this shift, this term here is from the flat space limit, okay, but there can be corrections to this shift right here. Okay, but at this order, we don't have to worry about the corrections, so we can basically forget about this for now. And if we assume a non-trivial profile only in the radial direction, then just solving this, finding the equations of motion for this, we end up with this equation here. Okay, and we can do an approximation where we drop this r to the fifth, okay, and we set this, like I said, we're going to set this constant equal to this, okay, and doing that approximation, we end up with this equation here. All right, now this, so this is basically the same as the radial Schrodinger equation for a 4D harmonic oscillator with frequency beta h over 2 pi alpha prime. So basically then, we just set this term here then would correspond to the energy. We put that on the left-hand side. And this term here is the energy for the harmonic oscillator. So the lowest value has n equals 0. We just substitute that in, and you find that to this order, then the Hagedorn temperature has the leading term plus this 1 over 2 pi. So that's those terms. Higher order terms. So now I dropped this term before, let me bring it in, okay? And now let me also worry about sort of corrections to this 0-point shift, okay? And now what I basically have is I have a perturbed Hamiltonian where this delta H is basically this term up here, okay? So Zohar was using Peskin and Schroeder, okay? I can use actually Griffiths, okay? I can open up my favorite quantum mechanics book. And I can find that I can compute, say, the first and second order corrections to the energy from this term here. And you find these very simple expressions. Okay, so on the left-hand side, we have, this is the term I would get, but this would be the energy. And we should set this term over here, but now with a correction for this 0-point shift. Okay, so how do you get this correction? Well, okay, so we started by basically taking an inspiration from the plane wave result. Okay, so the Hagedorn temperature was computed for the plane wave in 2003. And in that case, what they found is effectively this delta C is given by this beta squared times the log of 2 divided by this term here, multiplied by a number, okay, which I'll call gamma. In their case, their number was 2, okay, for the plane wave. So if I take this result, okay, and basically substitute it back into this equation and solve for the Hagedorn temperature, okay, I find this result here. Okay, now the thing to take out of this is you notice that there's gamma dependence here, okay, but there's no gamma dependence in this third term, okay. And actually, since we're only going up to g equals 2.25, this term is actually going to be bigger than this term anyways, okay. So if we look at what this gives us, if we just substitute in numbers for this, we find that we get this expression here. And if you recall the results that we had, we found from our quantum spectral curve that this coefficient here was equal to this. Okay, so this seems to match. Okay, and since this now matches, let's now take this as a given and go back and look at the term before. And in that case, then you find then you get this expression that looks like that. Okay, and well, sorry, this was our result for this is the result we get from our fitting from the curve. Okay, and if we set gamma equals to 4, we substitute it into here, and we get this number here. Okay, and you can see that it matches. Okay, so that was very encouraging. So now we can go on to ABJM. Let me just say a few words about that. So in ABJM, as you probably all know, is a UN cross UN, n equals 6 Stern-Simons theory at level k and minus k. I didn't write minus k. So for large, our large Atuf parameter would be n over k, where k is the level, and it doesn't matter at the orders we're going to be at, but if we ever get to higher orders, we should take into account a minus the 24th. And this should be dual to type 2A string theory on ADS4 cos CP3. Okay, well, so we can basically play the same game we did, and since we now have a string theory on this curved space, we can play the same game as we did before. And if we do that, we're going to end up with a 3D harmonic oscillator. And the effect of that is that this equation gets a 3, and so the Hagedorn temperature at the leading term comes 3 over 8 pi. And making a similar set of assumptions for n equals 4, that we have some correction term, which is this log 2 times this gamma times this beta squared, then the Hagedorn temperature goes like this. Okay. And if we set gamma equals to 3, we get these numbers here. And then in our second paper, okay, and this took a huge amount of computer time, the ABJM QSC result, we got this. Okay. And so you can see that the numbers are in agreement. Okay. How much time do I have?
For 9 minutes, including questions.
9 minutes, including questions. Okay, so in any case then, for general D, this is what we believe the result will be for general D. Okay, now we basically only have, there's basically only 3 examples. Okay, 2 we solve for, and the other one we don't know how to do. Okay, so anyways, this is a prediction. If we ever figure out how to do the ADS3 case, okay, this is what the Hagedorn temperature will be. So anyway, and that turns out to be very hard to do on a quantum spectral curve as well. So, all right. So let me try and give you some motivation for what this value of gamma is, and this is a nice argument that's due to Harmark from earlier this year. So let's go back to this mass term that we had for the winding mode. Okay. So if we write this down, we remember I said that it was 1 plus r squared, beta squared over 2 pi alpha prime minus these terms here, this beta squared dependence here. Now this expression, as it's written, is not obviously covariant. Okay. So what we want is we're going to consider a time-like killing vector v mu, where the component along the tau direction basically is going to be beta. Okay, so in that case then, we can write down something that looks covariant for this term and this term by taking g mu nu, because this is basically g00 here, v mu over 2 pi alpha prime, minus 2 pi alpha prime, okay, and then plus something else for this part over here. Okay, so this something else has to be absent in the flat case, because this is the exact result in the flat case. Okay. And it has to have a v nu term in it to account for the beta squared term here. Okay. And so basically the only thing you can put in that's going to work is some constant times r mu nu times v nu. Okay, now this should also be true in the plane wave case. So if we start with the plane wave, okay, then we'd find that the mass squared then would have this form right here, and the only terms that are going to contribute are going to be terms of the g plus minus, a g plus plus from this term here, okay, and the only term in the curvature in the Ricci tensor that's going to contribute is an r plus plus term. So we have this. Okay, so this is equal to that. You substitute it in. You find the you find the Hagedorn temperature for this. R is minus 8f squared. And so you find then that this constant to match the Hagedorn temperature is 2 log 2 over that. Okay, so that's what I said before. Now let's go to thermal ADS and use the same argument. Okay, now we just have an R00 term is the only thing that's going to contribute to here. And that's just equal to minus D times G00. Okay, and so that's the leading term here is the 1. The R squared is subleading. Okay, so we get a minus D, and this would correspond to gamma equals D. Okay, so that's what we claim that you're going to find. Okay, so now, however, this R squared term is going to affect the next correction, and I said there was no term in the next correction. Okay, but this can be compensated by an extra kinetic term, which you can put in like this. So this term seems to appear. It turns out this would be 0 for the plane wave, so you can't use the plane wave to figure out what this term should be. Okay, but such a term should appear. Okay, so well, let me. You said yeah. Let me skip over chemical potentials. So let me just come to my conclusions then. So basically, using integrability in the ADS-CFT, we've been able to find analytic expressions, at least for the first few terms in this large coupling expansion, for both n equals 4 and ABJM. It can be generalized to chemical potentials, to include chemical potentials. I did not show those results because of time. And so what we'd like to be able to do is we want to find more terms in this expansion. And there's been recent progress in the quantum spectral curve that can greatly improve the numerics and basically help confirm the predictions from the string dual. In particular, what they've been able to do is to go to much higher values of the coupling. So before we were around G equals 2, now they can go G equals 100. We should be able to pick off many more terms. Another thing they can try doing is perturbing away from the plane wave limit, where you know the answer exactly. That's something else we're trying to do. And however, so at the end of the day, we're doing these calculations. Okay, we're doing things numerically. We're finding numbers like log 2. Okay, and if you go further, I'm for sure you're going to find zeta 3s and zeta 5s and zeta 7s and things like that. Okay, but we still don't know how to actually extract this from a worldsheet computation. Okay, so we can get very accurate numerics. Okay, where we know what the answer is, but we still don't know how to pull this out from this. And this, of course, involves the usual problems when you have background Ramon fields and worldsheet fermions. So anyways, thank you for listening.
Questions?
I wonder, you gave this analytical results, right? And at least at one, you said that it's kind of just directly geometrical interpretation. The others two, I mean, could be interpreted.
Sorry, say this again.
I mean, when you got this analytical results, and I believe you mentioned at least for one that it has geometrical meaning, right? I mean,
well, you mean because we're doing this on a string. We're doing it with an ADS5 target space.
Right, but
if you put in chemical potentials, then you worry about the S5 target space. Well.
Right, but it's just for this particular example, or other coefficient also has an interpretation.
Well, the subleading terms that yeah, no, those also result from the target space.
I see.
So yeah.
Does using Green-Schwarz?
I think I've tried. In fact, everything I've tried is with Green-Schwarz. But the problem is that so Green-Schwarz works perfectly for the plane wave. Okay, but I run into problems with, and I haven't figured out how to get them out. Because that's what I thought I would want to do. There was an argument made, if I can show once. I have slides. Just in case someone asked. So actually, there was sort of an argument about how to at least extract the leading term from the worldsheet. Okay, so the idea is the following. So if you think of the full 10-dimensional space, okay, then basically you have a string that's wrapping around the tau direction. And you can sort of choose like term directions where you choose it, say, you take a tau from here and you take one other direction from the rest of these 9 minus d directions, okay? So to leading quadratic order, the H Wiltshire bosons basically divide into d bosons with a mass that looks like this, and 8 minus d that are massless. And there should also be 8 Wiltshire fermions with some masses, which I'll call nu I. I runs from 1 to 8. Okay, so then you can try computing the 0-point shift. Okay, and that's what these people did. And so this is a contribution from the bosons. This is a contribution from the fermions. And so then you get a term like this. And the thing is that if the sums of these nu I squareds are not chosen properly, you're going to have a logarithmic divergence. Okay, so you say, well, that determines that these guys have to equal this to cancel this log divergence. Okay, and so then you would get this minus d, which is what you want. However, okay, when I tried to actually do this for Green-Schwarz, I can't get this to work. No, so it might be I'm just not good enough. Something like that. But and I don't. They just made some argument. Well, and we would want to know what these are, not just their sum, but each individual term, because in order to go to higher order terms, we're going to need the numbers. And so I don't know how to do it.
Well, let's thank Joe again.